in considering how oscillatory or a sinusoidal applied force can affect, let's say, a pendulum, we've set up the differential equation. We've seen that the differential equation is a non-homogeneous second order linear equation. We've solved the equation, we got the solution. Then we looked at the way the solution is going to behave if the oscillator is initially at its equilibrium position, moving with the velocity v0. Doing some straightforward calculations, we obtain this solution where we have a sine oscillation with a certain amplitude and frequency equal to the natural frequency of the oscillator, superimposed on a particular superimposed on a part of the solution that has an amplitude that gets larger as omega naught and omega 1 get closer, and is some combination of the cosine of omega naught and cosine of omega 1 functions. And we're trying to look at the behavior of the cosine of omega naught and plus the cosine of omega 1. So we're going to look at this expression, cosine omega naught t plus cosine of omega 1 t. Now, we're going to use the trigonometric identity in a minute, but let's first get a picture of some tricks that we're going to play so we can get a better handle on the behavior of this sum. Now, if we have omega naught and omega 1, which are just numbers, they're angular frequencies, and I've written this so that omega 1 is greater than omega naught. It could be the opposite. But the point is that we have omega naught and omega 1 on a number line. Then, right halfway in between, we have the number that represents the average of omega naught and omega 1. And the distance between the average and omega 1 is half the difference between omega naught and omega 1, since the average lies halfway in between. From here to here is half of that difference. Okay, and on this side, of course, omega naught lies at half the difference between omega naught and omega 1 on the other side of the average. So that we have omega 1 is the average, meaning the average of the two frequencies, angular frequencies, plus half the difference of those angular frequencies, whereas omega, and I wrote omega 2, and that should be omega naught, will be the average minus half the difference. Now, instead of writing out average plus half the difference, average minus half the difference, and so forth, I'm going to write omega bar equals omega naught plus omega 1, omega 1 over 2. That's the average. And I'm going to write beta equals half the difference. So I'm going to call that omega 1 minus omega naught over 2. So that's half the difference. Okay, how does that help us? Well, then we know that omega naught is going to equal omega bar minus beta, and omega 1 is going to equal omega bar plus beta. And now the cosine of omega naught t is going to equal the cosine of omega bar minus beta times t. And I'll distribute that, omega bar t minus beta t. And of course we do have the formula for the sum or the difference of two angles here, the cosine of the sum or difference of two angles, which we talked about just in the last clip. And we can also write cosine of omega 1t equals cosine of omega bar t plus beta t. And we have a formula for this. applying the formula, and you need to write out the formula and apply it to this expression and to this expression. I started to do it over here. I'm going to cross that out. I just didn't have room to write it out. That was ignorant. Okay. Applying those formulas and knowing that the cosine of negative beta t is the same as the cosine of beta t, the cosine being an even function, and you should know that just based on the trigonometric but the circular model of the sine and cosine functions. The sine of negative beta t is going to be the negative of the sine of beta t, and that's going to make this term plus, and this is going to come out minus, and you just need to work through the details of that, helping you to hopefully better understand the behavior of sine and cosine functions and apply them to the way you think about solutions to differential equations. Remember that we're looking at the behavior of cosine omega naught t plus cosine of omega 1 t, which means we're going to add this expression to this expression. Now, when we add these two expressions, we see that these expressions here are of the same sign, whereas these two are of opposite sign. Now I'm going to get something that's different than what I see in your textbook, and then I'm going to try to reconcile it, and if I've got a mistake, we'll take the mistake and maybe learn something from it. But I, right now, don't think that I've made a mistake. Okay, so I'm going to hazard a guess that I didn't make a mistake, and that when we add these two, we get this. Now, your text uses a different formula for the cosine of theta 1 plus theta 2, and I'll take a minute here and examine it in just a minute. But if the formula I've derived is correct as I derived it, and I've checked it out with a simple example and think it is, then this is our correct expression for the sum of these two terms. We'll make a slight digression in the next clip, and if we need to correct this, we'll do so. And then we'll continue with putting this together into an interpretation of the behavior of this oscillatory system.